So, we saw a bunch of guidelines basically, which I use the word best practices for instance. But how do these guidelines help? End of the day, it should help a designer who is based out of Chennai, it should help a designer who is designing from Michigan, it should help a designer who is in Auckland. So, basically across the world, wherever a designer is trying to design something, they should have an insight into manufacturing or assembly. What we have discussed now is the assembly perspective. The designer a priori should have an information on what might happen in the assembly situation. In other words, I would rather put it this way: if you have two assemblies, assembly 1 and assembly 2, but it is the same product, functionality wise both of them do the same thing, do the performance in the same time, but they are two different assemblies. One has 3 components and one has 5 components. So, you want to evaluate which assembly is better. How would you go about quantifying this assembly is one of the important stuff, and how would you compare them. So, we saw certain guidelines saying do not do this in an assembly situation, or rather do this in an assembly situation, because there are two major activities in an assembly. What are those? Handling and insertion. Okay. So, we saw some set of guidelines for handling, some set of guidelines for insertion. But how do we convert this into a quantifiable sense? How do we formalize this learning? Right now, it is only a set of guidelines, but we need to formalize this so that anyone can use it, let us say over a software or as a legacy document, someone should be able to use it. That is what this slide basically tells you. Currently, the guidelines, they do not account for the elimination or redesign of a part. It just says okay, it is good or bad, but sometimes that is not sufficient for us. How much is it bad? What else should I do to fix this error? That could be one thing. And there is no relative ranking at this point. You are not able to compare two different assemblies, assembly A and assembly B, in a quantifiable sense. Subjectively you might be able to do, that is what I guess we would have said somewhere. I want to be able to quantify it, not qualitatively say this is better. Quantitatively someone should be able to say the assembly B was better than assembly A. So, what are the factors that goes into quantifying the fitness of an assembly is something that we are. So, these are just a set of rules or guidelines that needs to be followed. A designer with this information is any day better than a designer without this information. But how can you generalize this understanding, how can you formalize this learning is what a DFMA tool is all about. Yeah, so the approach that provides a designer with an organized method. So, this is step 1, this is step 2, this is step 3, and then you get a metric for the assembly, and then you will be able to compare these two assemblies. So, it is an organized method to design a product for easy assembly and be able to evaluate it and compare it. So, what do systematic design for assembly mean, or what are the different steps in that? What do you think out of the few guidelines that we discussed are quantifiable from an assembly perspective? Number of parts we did not discuss as a assembly criteria yet, but yes, the answer is yes, but we have not discussed that as a guideline, because you can never give a guideline for number of parts. You can give a guideline for the relative number of parts, but not for the number of parts per se. So, from a part handling perspective, these are the things that we discussed yesterday: symmetric, non-symmetric. If you cannot make it symmetric, make it pronounced, okay, extra asymmetric, and prevent jamming, okay. Tangling, avoid very small designs, flexible designs, sharp designs, slippery designs. In an insertion sense, make sure that you have access to the part that you are inserting until the insertion is over, okay. And a hole in the work, sometimes air might get locked, that is one that I am talking about. Difficult to insert because this particular length matches this length, that is not what you want. You might want this a little longer, then you are fine, okay. So, now with this can you tell me what of these guidelines that we spoke about can be quantified? Or this is just a few guidelines, but you can also think of something else. Number of parts could be one, but something that we discussed yesterday itself in the pen, you decompose the activity of assembly into two, one is handling and the other one is insertion. Well, practically the size, the symmetry, how symmetric it is, how anti-symmetric it is, how big it is, how small it is, what size of a shape it is and all that. Okay. So, basically symmetry can be quantified or need to be quantified, size, the weight, what is the thickness, basically weight includes thickness also, what is the level of flexibility, what is the geometry, are there chamfers, insertion time, this was something that was discussed yesterday, restricted access, sometimes it is very difficult. Okay. From a serviceability perspective, this becomes very important. Imagine that someone put a spark plug, where you need to go underneath the chassis of the vehicle and you need a special tool to remove it. Half of the automobile market will suffer. Okay. So, restricted access, and there are a lot of other things as well. Okay. So, these are some guidelines, for instance, symmetry, size, weight, these are stuff that we discussed in one sense. Because in the example when I explained, I told you that the pen example, the cap I was able to handle, but not always you are going to have something, a part that you can handle using a single hand. Sometimes you might want two hands, sometimes you need a crane. For instance, if you have seen these metro train construction, okay. So, basically it is an assembly, they do not build it, okay. They have all these concrete stuff, only the pillars are built per se and your entire track is put together. Okay. So, if you see the Katipara junction, underneath that they had stored all those stuff, they are also made out of concrete anyway, and then they bring and just assemble them. Okay. But the one on the front side will be marked front, or there is some numbering scheme that they have, because they are not the same. Okay. Because the next one needs to have the a holder for the next block to come and fasten into it, whereas on the other side it will have a hole so that it can go and plug itself into the preceding block. Okay. So, imagine that the crane lifts it all the way up in the wrong direction and then realizes that it should actually be in the other way around. You understand what I am saying? Okay. So, there will be some kind of a marking on that saying this is the front side and this is the back side. It goes this way. If you see many times in your cell phones, it is very clearly mentioned which way your SIM card goes, correct. Your SIM card has a small like a cut, okay. It is not a perfect edge, right. In one edge it has a cut, basically it is a directional notation, it says this is the way. So, you can see many of your the road signboards, they are beyond language, that is why they are signboards. Okay. Someone from Germany comes and can also write, I mean riding in Chennai traffic is a different story, but anyone coming from Germany also will understand the signboard. Similarly, when you go from here to anywhere in the world, you will understand the signboard from the sign. You might not understand what is written at the bottom, okay. The language might be different. So, that is a basic idea, it should be universal, the idea that you come up should be universal. Okay. So, yeah, the reason that I gave the example of the metro train was it is large, but even there it is the same story. Assembly has two things, one is handling the part and the other one is inserting it with the other stuff to attain or to accomplish your assembly. So, people over the past have analyzed each of this and much more elements that are part of handling and assembly, and they have done some detailed study which has gone into building this DFA tool. Okay. Today it is a commercial software, but there are also not open source, but for research purpose some tools are available for free. So, how do you quantify an assembly? Okay. This multiple times I have told in my lectures right now. So, let us assume that you have two alternate assemblies for the same product, okay. And how will you go about justifying one assembly is better than the other assembly from different perspective, from the ease in which the assembly can happen, or the ease in which it can be serviced, or what are the difficulties if you want to, if you do not want someone to disassemble it in an easy manner. Okay. How will you, what are the difficulty levels, which one is more difficult? So, it is not always easy, it could also be difficult. For instance, if any of you use a Mac desktop, okay, you will see in the monitor, which is also integrated with the CPU, you will never see any screws. Okay, it's nice. It's the aesthetic finish is awesome. You see, it's a single integrated setup. There is no additional CPU. There are no wires. There is only one wire that connects the monitor to your plug point. But it looks great. But once there is a problem, you cannot just open it just like that. There are no 4 screws that you can open. You actually need a vacuum puller that you will pull on it, and then you will have to pull it. So, you need a skilled labor to do that. Okay. So, there might be a reason why Mac did that. Probably that is one of the most nice fastening scheme. Okay. But from a removal perspective, it is difficult. Maybe there is a reason for that also. So, it is always not ease, but also the difficulty could be a stuff. Then the assembly efficiency is something that you want to look at. So, efficiency is not a new word for you, right. So, we have seen efficiency in different senses. It is basically what people say is output by input. That is you give this much and this is the output, right. So, there is something called ideal. Okay. What would be your ideal efficiency? 1. So, basically I give this much input, I get the same output, but that is not possible. So, efficiency is usually less than 1. Okay. There is always some loss, that is what your law of momentum says, right, or law of conservation says. In a similar sense, what do you think could be an assembly efficiency? You can always say this assembly has an efficiency of 0.6, but what could be, because assembly means it is a ratio, output by input, output over input, right. So, in an assembly perspective, what could be an efficiency?
So, we could be giving some weights to all of the components that we just discussed, and based on these weights they could be given some marks. So,
okay,
it's kind of like calculating the CGPA. So,
correct, but that is just one. In CGPA, I know the maximum you get, I mean I am just giving an example, is 10, then I say you get 8. So, the CGPA calculation is only the top, the numerator, the denominator I know is 10. So, then it is a ratio, you are right. The maximum CGPA that you can get is 100%, which is 1 primarily. In a similar fashion, what could be the numerator, what could be the denominator? Numerator is one sense what you are saying is right.
if the marks are given from 1 to 5, so maybe we can take 5 as the highest possible marks and use that as a denominator.
Okay. So, basically that is the ideal, yeah, okay, but that is okay, it is similar in idea, but then what we figure out is, let us not worry about this n min yet, we will come back to that. The one that I am talking about is this guy. So, it is going to be in terms of time. What it says is there is a ratio TA divided by TMA. TMA is the estimated time to complete the actual assembly or the actual product that you have right now, okay, that is your denominator, and the numerator is, this is kind of the ideal stuff, it is a basic assembly time which says the time averaged over the number of parts that you are looking at without any handling or insertion difficulty, it does not account for that, okay, it just says okay, there is a bolt and there is a nut and then you are going to tighten it. Someone asks what kind of a nut it is, what kind of a bolt it is, and then what are the size. Someone has made a study and then they have given a mean value and they have given an deviation around it in terms of time. So, sitting on a computer, you can say if my product has two components, two parts, and it is assembled using 4 screws without having the product feel, without physically feeling the product. On computer you can tell how long will it take for this assembly to be done. Okay, that is what this says. So, what it says is this is the physical time, okay, of the actual product that you have. This is the ideal time that comes from a theoretical perspective. So, always it is likely that this number is less, because it does not account for handling, insertion and fastening, okay, and this guy is likely to be more. Okay. So, that is why the ratio is always less than 1 in that sense, and n min means the theoretical minimum number of parts. Okay. So, we will see, meaning you have to just multiply this with the theoretical minimum number of parts. We will see what a theoretical minimum number of parts is, because this is something that you hit upon. You said that the number of parts, can that be a gauge? In one sense, that is what they are coming up with. They are saying at under what conditions will you say that you need to have 2 parts to do this? Can't you join these 2 parts? Can't we merge these 2 parts? Under certain conditions they say you need to have 2 parts. So, that is what is called the minimum, theoretical minimum number of parts. See, for practical purposes you might say that I do not have a vendor who can merge these 2 designs and give me, okay, these 2 components into a new design and give me. But there are plenty of vendors who can give me part A and part B. Now, I have a design which merges part A and part B, but I do not have a vendor, or the vendor is expensive, but cost wise, it is much easier for me to make A and B separately. For practical reasons you might have any reasons for that, but that is why it is called a theoretical minimum number of parts. So, it is ideal. Theoretically on paper this is what it is. You could have plenty of reasons from a practical perspective. So, we will see what that theoretical minimum number of part means. It says satisfying one or more of the following criteria. Okay. So, what the first one is, the part moves relative to all other parts that are already assembled. Okay. It moves relative to all other parts already assembled. Then it needs to be a separate part, correct? If a part is going to move relative to another part, then I cannot merge it. But the question is, if you have multiple parts and this guy is rotating only with respect to one part, okay, you might still be able to integrate it with another part. But then what happens, that entire part, the integrated part rotates with this, and you will have to figure out whether it is fine. That is why it says it moves relative to all other parts that are already assembled. Then for sure it should be a separate part. The part that is rotating with respect to all other parts have to be a rotating part, have to be a separate part, otherwise there is scope for integration. So, you can always say, oh, I can integrate it, but then there is something that comes in between. I will have to integrate part number 1 and part number 3, whereas part number 2 is coming in between, and it is very difficult to, yes, there is difficulty, but theoretically it need not be a separate part. Okay. However, one part is moving with respect to all the parts, then obviously it needs to be a separate part. So, that is bullet 1. The bullet 2 is the proper functioning of the product requires that product to be of a different material. This is something that we spoke about yesterday. You take any strength of materials based software like finite element software and stuff like that, they all talk only about the performance. They never spoke about, you are giving me 2 different material models, is it possible to merge them? That is not a rule, that is not within the scope of a finite element. Finite element just ask for the property of the material, and it will make sure that the loads that you apply, and give the stresses or the response such that you can see whether the material has failed or not. It will never say can you assemble, is it possible to merge these two guys, it is possible to tighten these two different materials, two different components made out of two different materials. Okay. So what this says is the proper functioning of that product requires a part to be of a different material than the adjoining material. So let us say for instance one example that is cited is for electrical reasons I might want to have it in a different material. Okay, either it should be conducting or non-conducting material, it should be of a different material. Noise vibration isolation, in order to do that I need to have a rubber material so that it damps. Okay. Ideally you might want to, it can be a continuation of a, I don't know, like a steel material, but in order to isolate the noise and vibration I put a rubber material. Okay. So then it has to be made out of a different material obviously, then it can be a different part. Okay. The third one is these criteria need to be applied without accounting for general design requirements. Fasteners generally do not meet the above criteria and will qualify to be eliminated. Okay. See, for instance, when you look at it in the ideal assembly case, fasteners will not be counted. It will say they do not need to be two different parts, I can always weld them. Okay. Hence, fasteners will not play a role. However, in reality you have 4 screws, each of them will take half a minute, 2 minutes is there for one assembly. If you are making 100,000 assembly per day, it is 200,000 minutes gone. Okay. But that in the ideal case it will not be accounted for, that is all. Okay. And these criteria, that is what I said, these criteria need to be applied without accounting for general design consideration. You cannot say, oh, there is a manufacturing issue, hence I am doing it. No. You will have to look at assembly as a standalone assembly and make these comments. Okay. You cannot say, that is why it has to be on a software per se. You cannot apply your legacy thought on it and you cannot say this is not possible. It does not matter from an assembly perspective, unless this part is moving with respect to all other parts, it need not be a separate part, that is all. Okay. So this is what is the theoretical minimum number of parts. You can apply these criteria and you can find out how many different parts is a must, you add them up and that will be your theoretical minimum number of parts.